This is a short video to cover some of the topics that I wasn't able to do in class. So in this lecture, I'll speak about some properties of subgaussian random variables, and I'll also introduce a related notion of subexponential random variables. Now recall that in the last class, we looked at these equivalent characterizations or equivalent properties of random variables. So if x is a random variable that satisfies any one of these four properties, we showed that the random variable must also satisfy the remaining three properties. And in addition, if x has zero mean, then these four properties are equivalent to a fifth property, which is essentially a bound on the moment generating function. All right, and this is useful because at times we are not able to characterize random variables or we are not able to directly obtain bounds on the moment generating function or obtain a tail bound of this particular form. But instead we have a handle, or we can show bounds on the LP norm or bounds on the moment generating function of x square. So if we can prove any one of these four properties or one of these five properties, then we are also guaranteed that the remaining properties hold. And any random variable that satisfies these properties is said to be a subgaussian random variable. So in particular, we define this notion of a subgaussian norm, which was defined as the smallest k such that the expected value of e to the power x square divided by k square is less than or equal to 2. And recall that we wanted this k to be as small as possible because in some sense, if we have the smallest k, then that smallest k up to a universal constant corresponds to the smallest k1 in this particular tail bound. So in some sense, this gives us the tightest possible tail bound. So if k1 is the smallest possible, then the exponent, that is delta square by k square or k1 square for a given delta is in some sense the largest. So loosely speaking, it gives us a reasonably tight bound on the probability of this deviation. And the reason why this particular parameter, the subgaussian norm of x, is called a norm is because it satisfies all of the properties of a norm. Over the space of all subgaussian random variables, the subgaussian norm is non-negative, and this is equal to 0 if and only if x is equal to 0 with probability 1. So it's a trivial random variable which takes the value 0 with probability 1. And it also satisfies the scaling property that for any alpha in R, alpha time, the subgaussian norm of alpha times x is equal to mod alpha times the subgaussian norm of x. And it also satisfies this triangle inequality. Property 1 and 2 are fairly simple. Property 3 requires a little bit more of work, and I'll leave that to you as an exercise. And at the end of the last class, I gave the following exercise to find whether the following random variables are subgaussian. The exponential distribution, as we saw in class, is not a subgaussian random variable because there exists no finite k for which expected value of x square by k square is less than or equal to 2. The Gaussian and bounded random and any general bounded random variable is also subgaussian. And in particular, the subgaussian norm of a Gaussian is some constant times the variance, and the subgaussian norm of any bounded random variable is some universal constant times alpha, where it is assumed that the random variable is bounded between alpha and minus alpha. Right, so proving this, I'll just leave it to you as an exercise. Now let's look at some useful properties of subgaussian random variables. In general, if x is a subgaussian random variable, then x minus expected value of x is also a subgaussian random variable. and the subgaussian norm of x minus expected value of x, that is a centered random variable, is upper bounded by some universal constant times the subgaussian norm of x itself. And if x1 through xn are independent and subgaussian, then, and moreover each xi has zero mean, then for every set of real numbers a1 through an, the linear combination summation I equal to 1 to n ai xi is also subgaussian, and the subgaussian norm of this, as one would expect, is upper bounded by some universal constant times summation I equal to 1 to n ai square times the subgaussian norm squared of xi. So in this course, we are not particularly interested in these universal constants because ultimately it does not depend on the distribution, and really what we're interested and in many cases, particularly in applications such as data science, communications, and machine learning, what we're ultimately interested in is the dependence of the tail bounds on the number of random variables n and the deviation delta. So any of these additional universal constants are not going to be of particular importance, because in the end we are always interested in just trying to understand the behavior of these random variables. All right. This second part is particularly easy to see. I will not prove the first part, but the second part you can just obtain by using the 5 properties that we have seen earlier. So since we are looking at sums of or linear combinations of independent random variables, the easiest place to start is just by looking at the moment generating function. So let's try to use property 5. So let's look for any t greater than 0, the expected value of e raised to t times summation I equal to 1 to n ai xi. Just because they are independent random variables, you can write this, or in any case, this is always equal to e to the product I equal to 1 to n e to the power t times ai xi, and because they're independent, because these are independent, we can write this as product I equal to 1 to n expected value of e to the power t times ai xi, which now we can essentially just use the property 5, and an equivalent way of stating this is that it is less than or equal to product I equal to 1 to n, since each of these xi's, and in fact ai xi's, are also subgaussian. This is less than or equal to e raised to t square ai square times the subgaussian norm squared of each xi. Right? I'm simply using the fact that ai xi is also subgaussian, and the subgaussian norm of ai xi, where this is equal to ai square times the subgaussian norm of xi square, and I'm just using property 5. Alright, so this is equal to simply expected value of t square. I'm sorry, there should be a constant here, some universal constant. So this is some universal constant. So t square times some universal constant times summation I equal to 1 to n ai square times the subgaussian norm squared of xi. All right. And this holds for all t greater than 0. So the moment generating function of a zero mean random variable, if each xi is a zero mean random variable, then summation I equal to 1 to n ai xi is also a zero mean random variable. And this zero mean random variable satisfies property 5. Essentially, it satisfies property 5 with some constant k phi equal to universal constant times summation I equal to 1 to n ai square times the sum of the subgaussian norm of xi square. So therefore, we can conclude that summation I equal to 1 to n ai xi is also subgaussian. And it's subgaussian, therefore, since the subgaussian norm is defined with respect to property 4, we can say that summation I equal to 1 to n ai xi, the subgaussian norm of this random variable is in fact some universal constant times this c prime summation I equal to 1 to n ai square times the subgaussian norm squared of xi. So we prove property 2. Property 1 is also fairly requires a little bit of work. It uses the fact that this subgaussian norm is in fact a norm, so you use triangle inequality and then get a bound. But anyway, we won't worry about that. Okay, so just purely by properties 1 and 2, we have the following tail bound because we can just use the 5 properties of subgaussian random variables, and we can claim that if x1 through xn are independent subgaussian random variables and a1 through an are arbitrary real numbers, then for every delta greater than 0, we have a tail bound on the linear combination of xi's. So the probability that summation ai xi deviates from its expected value by an amount delta decays exponentially in delta square. So it's less than or equal to e to the minus constant times delta square divided by the subgaussian norm of summation ai xi. All right. So that's essentially a direct consequence of the two properties that we have just seen, centering and linear combination. Right. So this is called Hoeffding's inequality, and there are some minor variants of this Hoeffding's inequality. So one thing to keep in mind is that any upper bound on this particular denominator would also give a valid upper bound on this particular probability. So at times when we're either not able to compute this, or what we have is an upper bound on the maximum of these sub-Gaussian random variables, we can get slightly looser but still useful bounds. So one particular useful form is this. So we can write this as k times norm, the 2 norm of a squared, where what is k? K is simply the maximum over all I of the sub-Gaussian norm of xi, just the sub-Gaussian norm of xi. So this is called, in some books you'll find this particular variant of Hoeffding's inequality, but nevertheless both of them are equally valid. This is a looser bound than this particular bound. Same holds, and this holds for general independent subgaussian random variables, not necessarily identically distributed. Identically distributed, then this simply simplifies to k square times norm of a square, where k square is simply the subgaussian norm, or where k is the subgaussian norm of x1. Okay. Now recall that from property 2, we had an upper bound on the LP norm of a subgaussian random variable. So let x be subgaussian. In particular, just from the properties that we've seen, let's in fact assume that x1 through xn be independent expected value xi equal to 0 for all I. So all of them are zero mean random variable. And let's further assume that expected value of xi square equal to 1 for all I. So they're all unit variance random variables, and let's assume that all subgaussian. All right. Then we can prove that for all real numbers a1 through an and numbers p which is greater than or equal to 2, we have an upper bound on the LP norm of summation ai xi. So the LP norm is simply, by definition, expected value mod summation I equal to 1 to n ai xi to the power p whole to the power 1 by p. Now, since summation ai xi is also subgaussian, the LP norm, just by property 2 of subgaussian random variables, is upper bounded by some constant times square root of p times the subgaussian norm of the corresponding random variable, which is summation ai xi, and we've seen that this is equal to summation I equal to 1 to n ai square subgaussian norm square of xi under square root. Right? So this basically, this inequality just follows from the properties of subgaussian random variables and the fact that summation ai xi is also subgaussian with this particular subgaussian norm, or it's upper bound, the subgaussian norm is upper bounded by this some universal constant times this particular quantity. But this LP norm, as it turns out, is also lower bounded by the 2 norm of A. So in fact, we have upper and lower bounds on the LP norm of a subgaussian random variable or a sum or a linear combination of subgaussian random variables. And this is attributed to Khinchin. This is called Khinchin's inequality. All right. Okay, so those were some basic properties of subgaussian random variables. We'll see some applications of these bounds later on. But now I'd like to contrast these sub-Gaussian random variables with another example that we saw previously, particularly in your midterm exam, which was the Poisson random variable. Now, what you were able to show for Poisson random variables was that the Poisson random variables don't really have a tail bound that decays as e to the minus constant times delta square, right? For the Poisson random variables, what you were able to show was that the probability that x minus expected value of x greater than or equal to delta, so this decays as e to the minus some c1 times delta square, where this c1 can potentially depend on the mean of the Poisson random variable, but this bound holds true for small enough delta, for delta less than or equal to the mean, and it is instead upper bounded by some constant times delta for delta greater than the value of x. So we don't have a sort of, I'm sorry, these should be negatives. So we don't really have e to the minus delta square behavior for all delta greater than 0. This only holds true for sufficiently large delta. And so in fact, the tails don't decay as fast as a Gaussian, but instead these decay much slower. They decay exponentially in delta, but not exponentially in delta square. So these classes of random variables are what are known as subexponential random variables, and it's closely related to this notion of sub-gamma random variables. You'll see these two different notions sometimes being used interchangeably. So just as we had for the sub-Gaussian random variables, we can sort of characterize them using equivalently using either tail bounds or the moment generating function or the LP norm. So if x is a random variable, then just as before, the following properties are equivalent, and for each property, the ratio of two of these constants ki and kj is upper bounded by some can be upper bounded by some universal constant. So so for example, if the probability that mod x is greater than or equal to t is upper bounded by e to the minus t divided by k1. Now let's just maybe in the side, let me contrast this with what we had for sub-Gaussian random variables. So the right hand side for sub-Gaussian random variables behaved as e2 times e to the minus t square divided by k1 square. We call it k1 bar square perhaps. Right. And the second property is that the LP norm is upper bounded by some constant times p. For sub-Gaussian random variables, we saw that it was some constant times square root of p. So that's a difference. And the third property now is that the expected value of e to the t times mod x is upper bounded by e to the k3 times t. And for this holds true only for t between 0 and 1 by k3. For the sub-Gaussian random variables, we were bounding expected value of e to the t square x square, and that, as we saw, could be upper bounded as e to the k3 square t square. Right? And that held true only for t such that mod t was less than or equal to 1 by k3 square. Property 4 is the expected value of e raised to mod x divided by k4 is less than or equal to 2. For sub-Gaussian random variables, we showed that expected value of e raised to x square divided by k4 square was upper bounded by 2. And similarly, if expected value of x is equal to 0, then the four properties are equivalent to saying that expected value of e raised to tx, that is the moment generating function, is upper bounded by e raised to k5 square t square. But for sub-Gaussian random variables, this was true for all t greater than or equal to 0. But now this holds under a slightly more relaxed constraint that this holds true only for t satisfying mod t less than or equal to 1 over k5. Right? And so these are the properties that we had for sub-Gaussian random variables, which is different from what we can prove for sub-exponential random variables. So any random variable that satisfies one of these four properties, or one of these five properties, if expected value of x equal to 0, is said to be sub-exponential. And just as before, we can define the sub-exponential norm, just as we defined for sub-Gaussian norm, we can define the sub-exponential norm as the smallest k4 that satisfies this particular inequality. So the sub-exponential norm for a sub-exponential random variable x, the sub-exponential norm x psi 1, this is defined as the smallest constant k such that expected value of e raised to mod x divided by k is upper bounded by 2. Right? If you think about it a little bit, you'll see. Okay. So just as before, this also happens to be a norm. Satisfies all the properties of a norm. If you think about it carefully, if x is a sub-Gaussian random variable, then just by property 4, x square is sub-exponential, and in fact the sub-exponential norm of x square is simply equal to the sub-Gaussian norm of x, the whole square. All right. So that is easy to see. But a slightly stronger statement holds, something that I will not prove here. If x square is sub-exponential, then x is sub-Gaussian. All right. And you can see that again the sub-Gaussian norm and the sub-exponential norm should necessarily be related in this particular way. Right. So as before, just by the property of the norm, if x is sub-exponential, then a times x is sub-exponential implies that a times x is also sub-exponential, and the sub-exponential norm of ax is equal to mod a times sub-exponential norm of x. And just as we did for Hoeffding's inequality, you can prove an exponential tail bound for sub-exponential random variables. I'll just state the result, but I will not officially, I will not completely prove this particular result. So this is called Bernstein's inequality. And it states that if 1 through xn are independent, zero mean and sub-exponential, then for all delta greater than 0, we have the following tail bound on any sum. In fact, you can also generalize this to any linear combination, summation I equal to 1 to n. Let me just state it for a general linear combination. Summation ai xi, probability that this is greater than or equal to delta is upper bounded by 2 times e raised to minus some universal constant. Now it's not simple anymore, it is min of delta square divided by summation I equal to 1 to n ai square sub exponential norm of xi square and delta divided by maximum over I of mod ai times the sub exponential norm of xi. So you'll see that for sufficiently small delta, this term particularly becomes the minimum. For large enough delta, this term becomes the minimum, and therefore you see two different kinds of behavior. So for small delta, so a sub-exponential random variable, you look at probability mod ai xi greater than or equal to delta. Behaves somewhat like this. There are two different regimes wherein for small enough delta, the x-axis is delta, so delta less than delta star, it behaves like a Gaussian. basically the probability that this is greater than or equal to delta, decays as 2 times e raised to minus some constant delta square divided by some other constant. But for large delta, it behaves exponential, where so in the Gaussian tail regime it behaves like this, but then for larger regions, for larger delta, the tails are exponential. So sometimes this is called small deviations regime. And this, for delta greater than something, is called the large deviations regime. Alright, so that's it for this particular video. We've seen some properties of Gaussian and exponential distributions, sub-Gaussian and sub-exponential distributions, and we'll maybe in the next lecture we'll see some applications of these properties, the Hoeffding and Bernstein's inequalities that we've seen.